Welcome to my talk. My name is Ricardo Calix. I'm an associate professor at Purdue University Northwest, and I will be presenting the paper, SACIAT is where it's at, Insights into Backdoors and Debiasing of Cross-Lingual Transformers for Named Entity Recognition. We did this work in collaboration with IQT Labs, based in Arlington, Virginia. And like I said, I'm with Purdue University Northwest. So this talk is given for the Big Cyber at the IEEE Big Cyber Workshop for the IEEE Big Data Conference, Osaka, Japan, 2022. Okay, so this study has 4 objectives related to better understanding transformer models and NLP. Number 1, to determine if there's bias in a cross-lingual transformer model such as RoBERTa XLM, which I will sometimes refer to as XLMR. We applied this for the named entity recognition task. So this was a pre-trained model that was fine-tuned for named entity recognition and natural language processing. So the objective is to look at bias and backdoors, which is a hot topic in transformer models, and also to get, hopefully, to analyze the model to get a better understanding for it. Second objective is to provide a predictive explainability or interpretability framework that addresses the reasons why the XL model may or may not have bias. And then based on that understanding, to test this framework on different scenarios to evaluate its predictive capabilities and see how we can use it. Maybe, and so I'll discuss that. So the fourth objective is to consider implications of any insights and future research directions. So I'll start with just kind of some main findings, and then I'll get into the methodology, the experiments, and the conclusions, and the proposed methodology, of course. So based on experimental results that we did, we found that XLMR is not significantly biased in the named entity recognition task. And named entity recognition, of course, is recognizing the characters in the story or the location. So, for instance, Huck Finn in The Adventures of Huckleberry Finn, or just different characters in the story. The transformer model we use is not trained with a backdoor. However, we found a way to exploit, we found a way that we could influence the predictive capabilities of the model. So we found a way of a phenomenon that is happening in the model that allows us to control in a predictable way, the scores, how it performs. And so I'll talk about that. So we can positively or negatively affect the performance of the model. Okay, so based on insight from the experimentation phase, we exploit the language model structure already in the transformer to affect the recall scores, either positively or negatively. And I'll talk more about that. So in the context of this work, we focused on words and subwords, and we basically manipulated subwords to influence the model. So we refer to subwords as the attack word. So it just appeared, attack word just means subwords that can affect the recall score either positively or negatively. And we refer to as, when we affect the scores positively, it means that we improve scores, so we call that debiasing. When we affect the scores negatively, by dropping the score, we call that backdooring. So we affect the performance of the model. Subword is just basically, you can think of it as just a syllable in a word. So, Johnson, so son is a syllable, so we call that a subword. But subword has a context in transformer models, so obviously we're using that specific definition for transformers. To perform the experiments, so to perform the experiments, around 7,000 subwords were randomly selected from the 250,000 available subwords in the RoBERTa XLM tokenizer. So whenever you use a transformer, the transformer uses a tokenizer to create a vocabulary, basically. And this is a vocabulary not of words, but of subwords, of a type of a syllable that's created. And our experiment is to manipulate subwords to affect performance. So our experiments, initially, we just used a few subwords intuitively. Then we, based on some insight, we selected 7,000 subwords from the 250,000 to perform our experiments. These 7,000 subwords were individually concatenated to all named entities in the text to see if the subword would affect the named entity recognition model. And the results show that subwords can affect the named entity recognition performance either positively or negatively. Our scheme was very simple. Usually when you do an attack, like you think in images, you'll put in the image a cloud or some randomness, a Gaussian randomness, and that's an adversarial attack. Here in our context, we have NLP. So what we do is to insert the attack, the adversarial attack, is if we have a word like Jang, right, we'll add the word sun, so Jang Sun, and we make the last name instead of Jang, Jang Sun, and that just makes it, we change the name basically. But that's the attack. That's our way of adding the adversarial attack by adding the subword just to names, since we're working on the named entity recognition. So we tried this initially with 7,000 randomly selected words. We concatenated to all the named entities, and then ran basically the transformer on the text. We had the original text and then the modified text, and that gave us the original baseline recall scores plus the new recall scores. So since we selected 7,000 subwords, our intuition is that some words would affect positively, some would affect negatively, and then we could build a training set so that we could later on, as I'll describe, be able to predict which subwords can affect the model, and therefore create either our debiasing approach or our backdooring approach. To address the problems, now the issue with selecting subwords randomly is that you don't know what the outcome will be. So the goal was to not have to just pick words randomly, but to know, okay, if I select these subwords, I'm gonna get these results. And also the other issue is that we're using RoBERTa XLM, which is a multilingual transformer. So it means there's like 100 languages in the data set. If you're an English speaker or Spanish speaker and you're looking at Chinese words, you will not know what they mean. And so you won't be able to select the subwords. But with this methodology, it doesn't matter what language you speak, you can actually just automatically select the correct subword. So that's the idea for the particular attack that you're trying to do. So to address the problems with random selection, an automated subword selection approach was proposed. And this is the main focus of our work. This was based on machine learning. So a machine learning model is trained to predict subword candidates. This is a regression model that I'll describe later, but basically what this does is for every subword of the 250,000, we can predict what the recall score might be. And so therefore, we just rank all the subwords and pick the ones that we want, either the higher ones for debiasing or the lowest one for backdooring. Each subword needs to be represented as a feature vector, and the model should predict a score to indicate how the subword will affect the name NER performance. So this is where the transformer also comes in. We use RoBERTa XLM, which is a BERT type transformer. These BERT models are basically embedding systems. So you give it a sentence and it'll create embeddings for you. So, similar if you're familiar with word2vec, right, where we could represent each word as a vector of size 256. Transformer models are similar in that sense that you can give it a sentence, each word and subword in that sentence goes through all the layers of the transformer. And before the last layer, like a couple of layers before the last one, you have a pretty good embedding of the words, the subwords, the sentence, etc. So in our case, we just pick the subword that we want. Now, what's important with transformers, and that's different from other autoencoders, is that, or other embedding systems, is that it uses context and attention. So here, we don't just give the words, we give the sentence. So it actually understands, it looks at the sentence itself to create the embedding. So it's going to look at the context of what it, is it bank, rob the bank, or is it the bank of the river? And that's going to change the encoding. And so it makes it more powerful. And so we exploited this. The transformer model uses embeddings of size 768. So we can run all the subwords through the transformer and obtain the embedding. So it makes it pretty straightforward to create the feature vectors for our machine learning model. In general, by knowing the values of the embeddings of subwords in a transformer model, one can select triggers, subwords that will impact the overall performance of the model task, either positively or negatively. As such, this allowed us to develop a broad use backdoor scheme, and we tested this, and we found that it significantly affects the recall in both the NER task and a mask-based sentiment analysis task. I will mainly focus on the named entity recognition task, but we also tested this for generalization in another task, and that is explained in the paper. So the methodology, initially we ran some just kind of exploratory experiments. So the bias testing was performed by replacing English names from the data set with names from several foreign languages, such as Chinese, Spanish, etc. Two main sets of experiments were conducted. One set focused on more common languages, while the other set focused on less common languages. As far as the data set, we used the protagonist tagger data set. Given that this data set included labeled person entities for 13 classic novels. It was then straightforward to swap out the names of foreign language names. The swapping was done randomly. And these are the languages that we use. So this is the recall. The recall was the score that we use. It's defined as the total number of predicted correct entities divided by the total number of labeled entities. Okay, so as I said, when using transformer models in the context of multilingual tasks, words can be broken further into subwords. All right, and then this is just some information, some background. Talk about this. So in our work, we first selected the subwords randomly and then developed and tested an automated subword selection approach. A machine learning model was trained to predict subword candidates, and each subword needs to be represented as a feature vector, and the model should predict the score to indicate how the subword will affect the named entity recognition performance. So this was the model that we used. It's a regression model. It's basically made up of a linear function plus a nonlinear function. The nonlinear function is just a multi-layer perceptron, which is described in the paper as very straightforward. You give it an embedding of size 768 for the subwords, and then it predicts a recall score. So this, these are all the details of the model. You can see that in the paper as well. This is important. So the RoBERTa embeddings are of size 768. Therefore, the subword embeddings are of size 768, which results in a subword matrix of 250,000 by 768. After training, the regression model is applied to all the remaining subword candidates. The predicted scores are sorted, and the subwords with the top performing scores can be selected for debiasing, and we use the threshold of 0.85. So you can see here, in the next section, I will just discuss the results, and you can see them here. So initially, as you can see from the scores, the finding bias was difficult. In fact, we only found it in a foreign language called Seisiat, which was a very rare language only spoken in the island of Taiwan, but this allowed us to determine, give us the insight, right, and how this works. So it's an important finding. It gave us the insight that common subwords like sun added to words like Jang to create Jangson would improve named entity recognition results, whereas adding uncommon subwords would affect the performance negatively. This is the results that we got. So the yellow is the baseline. When we added sun, for instance, we debias and the scores improve and become green. When we added the Seisyat token, which you can see here, this one, the orange, the results go down. These are just some information on how different types of subwords will affect performance. If we use totally random, it's pretty bad. And then if we just use uppercase names, it's the best improvement in the best results. So we get a named entity recognition. Okay, so just because, I don't have much time in the video, the scheme for automatically selecting our model was here. This is when we selected 7,000 subwords. We applied it to the transformer, applied all of them, and the transformer basically gave us this, right? So this proves our intuition that, common subwords will improve performance, whereas uncommon subwords will not improve. So you can see here. So this showed that beyond sun and the Seisyat subword, we can definitely affect the named entity recognition performance just by adding or concatenating subwords. So now the question was, how do we select? As you can see, we don't want to select them randomly. Instead, we want to have a methodology. This is where we use the regression approach. And once we applied that, you can see that here, these are also Chinese subwords. And from a qualitative analysis, it was shown that these are all related to names for Chinese speakers. So you can see this further corroborates that sun, our intuition of sun, is a good one. So finally, we applied the model. And as you can see here, the model does improve the selection. So here we only have randomly selected words. A lot of them were below the baseline, which is this red line. Whereas with our regression model, you can see that we have most of the ones that we want above the red line. So in this case, we're only focusing on the debiasing task. And so we only wanted these subwords and we were able to obtain them. So here we only wanted the subwords that would improve performance considerably. And so our methodology allows us to do this by ranking the subword candidates. You can see that the performance of selection improved from 33% randomly to 65% when we use our method. All right, so in conclusion, in this work, bias and backdooring for named entity recognition were explored. Based on experimental results, a general framework for debiasing or backdooring of NLP models without the need for training was proposed. In general, by knowing the values of the embeddings of subwords in a transformer model, one can select subword triggers that will affect the overall performance of the model task either positively or negatively. All right, we tested this on the named entity recognition and the results seem promising and intriguing. And this concludes my talk, which has to be less than 20 minutes.